see here, this matrix is nothing but this ZPQ ABC. Okay, so ZPQABC, what we have written here in this particular block, this block is represented by this particular matrix ZPQAA, ZPQAB, ZPQAC, ZPQBA, ZPQBB, ZPQBC, ZPQCA, ZPQCB, and ZPQCC. Now here the diagonal elements, that is ZPQAA, ZPQBB, and ZPQCC. These are the self impedances of those particular elements in between the points P and Q with respect to the phase A, B, and C. So here the phase plays a very important role as we are seeing here the three-phase network. So as we are dealing with the three-phase network, what is important to note here is the phases. So phases we have represented by A, B, and C. So here you can see the phases A, B, and C are represented in this way. This particular point represents phase A, this particular point represents phase B, and the third represents the phase C. So I will write here, so this is the phase A, this is phase B, and this is phase C. Similarly, at the next point, that is, here you can see we have written P and Q. So in the previous unit, that is unit number 2, in our unit number 2, what we have done is, in unit number 2, we have solved the numericals related to the Z-bus formation by algorithm technique. So in that technique, we used to take add element 1, which is a branch, then add element 2, which is a branch or link, whatever it is. And we used to check from where that element has started and where it has ended. That is, the start point used to be P and the end point used to be Q. In this way, we used to frame the formulas. How we used to frame the formulas? We used to frame the formulas like for the addition of branch, we had two formulas. ZPI is equal to ZQI and ZQQ is equal to ZPQ plus ZPQPQ. That means what we used to do was, we used to apply this formula ZPI equal to ZQI for the off diagonal elements and ZQQ is equal to ZPQ plus ZPQPQ for the diagonal elements, right? So what was P and Q? P was our starting point and Q was our end point. So here also in this diagram you can see P and Q we have highlighted. So this is our starting point and this is our ending point. This is phase A, phase B, and phase C. So similarly here also we will write phase A, phase B, and phase C. The EMF respective to this phase A will be EPA, then here it will be EQA. Similarly here it will be EPB, here it will be EQB because this is the Q point, and here it will be EPC, and at this point Q point it will be EQC. Then we have the potential difference, which is there will be a potential difference between these 2 points P and Q, that we have written with the help of VPQA, VPQB, and VPQC. So VPQA is corresponding to the phase A, VPQB is corresponding to phase B, VPQC is corresponding to phase C. Similarly here in the right hand side you can see the current which is flowing through this particular element between P and Q. This we have represented by IPQA, IPQB, and IPQC. So whenever we are dealing with the three-phase network, we have to remember this thing, that in a three-phase network, the three phases, that is A, B, and C, this will play a very important role. Now, if I want to write the equation 1 in a compact form. Let us write the equation 1 in a compact form. How compact form we can write? Let us see. I will write here equation 1 in compact form can be written as. So if I want to write equation 1 in a compact form, how can I write? Let us see. Equation 1 in compact form can be written as. Equation 1 in a compact form can be written as. Let us see how we can write the compact form. For that we will go back to our equation 1. So this is our equation 1. In the LHS, that is to the left hand side of this equal to sign, we have VPQA, VPQB and VPQC. So this we can write in compact form as, let me write here, VPQ A, B, C, where P and Q are the 2 points of the element and A, B, C are the 3 phases respectively. Okay. Similarly, what is the second term? Second term is the EMF EPQA, EPQB, EPQC. So this how we can write? Let us write here. We can write here EPQ A, B, C. Then in the right hand side of the equal to sign, we have ZPQ A, B, C. Okay. So in the right hand side of the equation, we have the ZPQ ABC and which is multiplied by current, that is IPQ ABC. So in this way, we can write this equation in a compact form. Let us write this as equation 2. So equation 1 as well as equation 2 both can be stated as equation 1 and equation 2. Both are known as equation 1 and equation 2. Both are known as the performance equation both are known as the performance equation of a 3-phase network in impedance form. Okay. So this is the important part, that the equation 1 and 2 whatever we have written is known as the performance equation of a 3-phase network in impedance form. Okay. So is it clear everyone? This equation that we have written, both the equations, that is equation 1 as well as equation 2, this is known as the impedance form of representation of the 3-phase network. Okay. Now as we have completed the impedance form, let us now represent the 3-phase network in admittance form. So both the methods of the representation is widely used in the power system analysis, like the load flow analysis. That is, if we analyze the condition of a various buses in a power system network by using load flow analysis, there we require Y bus, that is the admittance bus. So we have to first formulate the admittance bus and then we have to start with our necessary calculations. In the previous lectures itself, we have stated that the name of this subject is computer application in power system. So what really computer application we want to know is that whenever we deal with large power system, these large power systems will have many buses. Like in our numericals, when we solve the numericals, we hardly take 4 bus or 5 bus system. But if we take a practical power system, 5 bus is very small, right? There may be hundreds of buses in a power system network. And at that time, if we start our calculations by using pen and paper, it will take days to compute the various parameters which are associated to that power system. So in that case, we require computer simulations, we require computer softwares where we can input all this database which is required to compute all the necessary calculations, and within a fraction of seconds we can get the exact results related to the loading of the buses, what is the condition of the potential difference between the two buses, what are the various parameters which are associated with these buses related to the power factor and related to other parameters which are studied in the power system analysis. So I hope now the things are becoming slightly clear to all of you that why the name of this subject is being given as computer application in power system. Because whatever we are calculating here, this forms the basis of the modeling in the formation of the computer softwares. So whenever we want to write a computer program related to the computation of the various buses, we will require this all the mathematical calculations that we are doing in unit 1, in unit 2, and now in unit 3. Okay. So these are all the parameters that we will be requiring. Now let us start with the next part, that is the admittance form of three-phase network. So this will be our today's topic. So today we are going to deal with the representation of three-phase network in admittance form. So this is what we will see today, the representation of a three-phase network in admittance form. So let us first draw the diagram, and with the help of the diagram we will see how the three-phase network is represented in the admittance form. So obviously in the admittance form we will use the letter Y, because we all know Z represents impedance and Y represents admittance. So here we will write Y, P, Q, A, B, C, where P and Q are the 2 points of the elements. So again, in the similar lines that we have drawn the block diagram of impedance, we will be making here admittance in this way. So this will be P point. So as we are writing this as a P point, here we have to write EPA, EPB, and EPC. And as we are writing the impedance form, now everything will be reverse with respect to the impedance. So as we are making reverse, we will flow the current from this side now. So current will be from this end, IPQA, IPQB, and IPQC. Okay. Now in the next end we have Q. So this will be the Q end. And as we are making the reciprocal of the impedance form, because we all know that admittance is the reciprocal of the impedance, right? So we will have to draw the reciprocal part in the right hand side. So let us see how we will draw the reciprocal part in the right hand side. So here we will have the, instead of the EMF source, Now it will be in the shunt part. Okay, so this we are drawing shunt mechanism in this way. So here there is somewhat less space, so I will draw here somewhat in the left hand side. So I will draw here as there is less space above this. So let us represent this by JPQA, then JPQB, and this by JPQC. So this is how we draw the diagram or the block diagram for the representation of the three-phase network in admittance form. Now, as we have written the various nomenclature in case of the impedance form, similarly we have to write the various nomenclature in the admittance form as well. So let us see how to write this various nomenclature. So here the new thing that you will be seeing is the J part, which is the source current. So instead of source EMF, now it will be source current. So let me write here. Below I will write here JPQA, JPQB, and JPQC. What are these? These are the source currents. So let us write here. These are the source currents in parallel with phase A, B, and C respectively. Okay. So this is the new part. Rest of the parts you all know. We have already written in the impedance form of representation. Only one more thing that will be new here is YPQABC. Right? So let us write here what is YPQABC here. So YPQABC is the three-phase admittance matrix. So I will write here it is the three-phase admittance matrix for the element PQ. Okay, so these were the two new things that we have seen today. So after this we will write the performance equation of the admittance form of reference. Similarly, like how we have written for the impedance form in the previous lecture, today we will be writing the admittance form of reference with respect to the performance equation. Like equation 1 and 2, these were the performance equation of the three-phase network in terms of the impedance form. Similarly, we will write the performance equation of the three-phase network in terms of the admittance form. So, is it over? Shall we move ahead? Diagram हो गया सभी का निकाल के? Okay. So let us write the performance equation or the mathematical equation with the help of which we are going to derive the equations. So we will write the equations in this way. Let us give the heading performance equation of three-phase network in admittance form. Okay, so let us write this performance equation of a three-phase network in admittance form. So we are going to write the performance equation of a three-phase network in the admittance form of reference. So let us write. So in the LHS we have here IPQ-A, IPQ-B and IPQ-C. So these are the three currents with respect to the point P and Q. These are three currents with respect to point P and Q with reference to the phase A, B and C respectively. Then we have to add the source currents which we have connected in parallel. So that will be JPQA, JPQB, JPQC. So these are the three source currents that we will be writing. Then this is equal to, in the block diagram we have the admittance matrix, right? So admittance matrix we will write in this way: YPQAA, YPQAB, YPQAC. So this is the first row. Then second row will be YPQBA, then YPQBB, then YPQBC. Similarly, the third row will be YPQCA, YPQCB and YPQCC. So this matrix will form the bus admittance matrix. Okay, so this will form the admittance matrix, and similarly we will have the voltages that will be VPQA, VPQB and VPQC. These are the potential difference between the points P and Q with reference to the phases A, B and C. Okay, so this is the, let's say, give this equation as equation 3, and equation 3 in compact form can be written as how to write it in compact form. Let us see. So this will be first IPQ ABC plus JPQ ABC. This will be equal to YPQ ABC and multiplied by VPQ ABC. So let us give this as equation number 4. So in this way what we have done is we have written the performance equation of the three-phase network in admittance form. So both the equations can be written. The third equation is the expanded form, whereas the fourth equation is the compact form. So by using these two equations, we can derive the admittance form of representation of a three-phase network. So in this way, we have completed the first two parts of this unit number 3. We have already discussed that unit number 3 will be more theoretical in nature, and the basics which we will be learning in unit number 3. This will be used to solve the numericals of unit number 5. Lecture itself we have said that what is the outcome of this particular unit. So at the end of this unit we should be able to find out Z bus 0, 1, 2, right? What is 0, what is 1, what is 2? You all have already studied this in EPS 2. So 1 means 0 sequence, then 0 means 0 sequence, 1 means positive sequence, and 2 means negative sequence. So what you have to make is you have to find out the bus impedance matrix with respect to the 0 sequence, positive sequence, and negative sequence. So this is what we are expected to do in unit number 3. So for that, the basics what is required that we have just now seen. Now we will start one by one to write the steps how to form this, to draw the positive sequence reactance diagram. I hope you all remember the procedure to draw the positive sequence reactance diagram. This you all have learned in EPS 2, positive sequence reactance diagram. Okay, this will be the first step for formation of this Z bus 0, 1, 2. Then second step will be determine the Z bus using algorithm technique. So this we have done in unit number 2. Then third step will be draw the 0 sequence reactance diagram. Draw the 0 sequence reactance diagram. So this also you have already done in EPS 2. So this will be your third step, and fourth step will be determine the Z bus using algorithm technique. So you can see here this step number 2 and step number 4 is repeating, right? But these both the steps are different with each other. How? Let us see. So Z bus from step 2 will be Z bus 1, that is Z bus with reference to the positive sequence component. Okay, and as we know that positive and negative sequence are equal to each other, as positive, because magnitude is one and the same, so positive sequence is equal to negative sequence with respect to the magnitude, right? So we are calculating here the magnitude only. That's why the Z bus 1 will be equal to Z bus 2. So you can see here Z bus 0, 1, 2 we have written. Out of this 1 and 2 you have already obtained. What about the Z bus 2? So the sixth step we will write here, Z bus from step 4 will be Z bus 0. Okay, so this is the sixth step. So if you will complete these 6 steps, then you will obtain the result of Z bus 0, 1, 2. If you want to write this Z bus 0, 1, 2 in a compact form, you can combine this step number 5 and step number 6 and write Z bus 0, 1, 2. Okay, so this is the procedure that we will be following. let us take one numerical and understand how this Z bus will be calculated in terms of the actual power system network. So this we have to understand by taking one numerical. Okay, so let us write the question of the numerical and then we will start with the solution part. So is the steps written everyone? Sabka ho gaya steps likh ke? Should we start with a numerical? Okay. So let us start with a sample numerical with the help of which we will be able to know how this Z bus 0, 1, 2 is formed. So let us write the numerical. So example 1. So first what we will do is we will first draw the power system network and then we will see how to solve this particular problem. So everyone please draw this. So here there is a power system network which is given to us in this way. This is bus number 1, this is bus number 2, so in this way the various components will be given. So in this way the things are given to us. This is a transmission line. So we will write here by T dot L. Okay. So this is what is given to us. Then a table will be given to us. So let us see what the table is given to us. It is in first part we have the element and second part given values in x1, x2, x0 and xg. We will see one by one what all these values are. So first they have given for the generator G1, then generator G2, then transformer. So I will write here transformer with T. So T, and then they have given the value for TL. So this is what they have given us. So values are in this way: 0.1, 0.1, 0.04, 0.02. Then again the same values: 0.1, 0.1, 0.04 and 0.02. Then for transformer they have given value as 0.1, 0.1, x0 also 0.1 and this 0.05. And for transmission line they have 0.2, 0.2 and 0.5. So in this way the database is given to us. We have to make use of this database and we have to solve the given numerical and find out the Z bus 0, 1, 2. So this is what the question is. So in unit number 3, as I have said, that mostly theory will come, but this is a numerical part which will be the base of your unit number 5. So for calculating the fault currents in unit number 5, you will have to calculate the Z bus 0, 1, 2 first, and then you will apply the formula according to the fault. Like if the fault is a line to ground fault, you all know what is the formula which is to be used. If it is a 3-phase fault, then again you know the formula that is to be used, and according to all this you have to find out the fault current. So this is what the question is, and the question is very simple: find Z bus 0, 1, 2. So this is what the question is given to us. With respect to the steps that we have written just now, steps what we have written, the very first step that we have written is draw the positive sequence reactance diagram, right? So once you draw the positive sequence reactance diagram, then you will be in a position to draw the or to visualize the things how to find the solution of this particular problem. So let us start with this solution. So what is the first step? First step is draw the positive sequence reactance diagram. So I will write here positive sequence reactance diagram. Positive sequence reactance diagram, right? So we have to draw this positive sequence reactance diagram, and then we will see what will be the next steps to find the Z burst by using the algorithm technique. Okay. So for this positive sequence reactance diagram, what is the procedure? Can anyone reply? Because in EPS2, you all have learned how to draw a positive sequence reactance diagram. Do you all remember it? किसी को याद है पॉजिटिव सीक्वेंस रिएक्टेंस डायग्राम कैसे बनता है? Yes, anyone? Do you all remember it? How the positive sequence reactance diagram is prepared? पढ़ तो लिया सबने EPS2 है ना? पेपर भी दे दिया, अब सबको पता है पेपर कैसे दिया, है ना? So this is the point which I want to make you clear. Don't just prepare your subject for the exam itself. Otherwise, you will not learn how the things are moving, and it will be difficult for you to secure a job in an industry, right? So if you want to do job in an industry, you have to be thorough with your subjects. If your subjects are thorough, then only you can sustain in the industry. Or else, if a new technology comes and if you don't know how the old one works, then you will not be in a position to understand the new one also, right? So someone has replied. Chaitali Gohani, very good. So draw the reference line, very good. So first we have to draw the reference line. So let me draw the reference line first. So this is my reference line. Then according to the number of buses here, we have to identify the number of nodes here, right? So this is the next step. So let me write here bus number 1, bus number 2 and bus number 3, right? After this, we have to connect with this reference one by one the elements, and we have to draw it accordingly in this way. So as we can see here, from bus number 1, there is a generator connected. So we are drawing the generator in this way. Then from bus number 1 to bus number 2, we have a transformer. So we draw the reactance of the transformer in this way. Then from bus number 2 to bus number 3, we have a transmission line. So we draw the transmission line reactance in this way. And finally, we have another generator which is connected to the generator G2. So we draw this in this way. Okay. ऐसे ही करते थे हम लोग, ऐसे ही करते थे कि दूसरा कोई प्रोसीजर अपनाते थे? Yes, please reply. Is it the correct procedure or there is some other procedure to draw the positive sequence reactance diagram? Is the correct procedure to draw the positive sequence reactance diagram. Now we have to write the values of the positive sequence component by using this chart. So the table which is given to us, we have to make use of this table and we have to write the various values which are given in this table associated with that respective component, right? So for component G1, let us check what is the value. So G1 and X1, this we have to follow. X2, X0, Xg are the secondary part. We don't have to follow it right now. Okay. So we will refer to the column of X1 and respective component here and write the values accordingly. Okay. So G1, X1, what it is? 0.1.
So I will write here 0.1. Now remember that this is a reactance diagram and all these components are given in reactance. So we have to apply the complex operator J. Is that clear, everyone? Why we have applied the complex operator J over here? Because all these are in a reactance form and reactance is associated with the complex variable J. Impedance, for impedance we need not apply J, but if there is a reactance we have to apply J over there. Okay, then from 1 to 2 we have a transformer, so we have to go to the transformer row and x1 column. So again it is zero point 0.1, so we will write here 0.1 J. Then from 2 to 3 there is a transmission line. You can see here in the actual diagram, from 2 to 3 there is a transmission line. So we have to go to the row of the transmission line and the column of x1. So transmission line value is given as 0.2 J. Then from 3 to reference there is a generator G2. So we have to go to G2 row and x1 column. So again it is 0.1 J. So in this way we have completed our positive sequence reactance diagram. From this positive sequence reactance diagram we have to draw the graph, then highlight the tree and cotree, because you know what is the procedure of finding the Z bus using algorithm, right? So we require a graph, we require a tree and cotree, and then only we will be in a position to start with the finding of Z bus by using the algorithm technique, right? So we will draw the graph here in this way. So we have 3 buses, so we will denote the 3 buses in this way, 1, 2 and 3. Then one reference line, so which will be replaced by the reference 0. Then we will connect one by one. So reference is connected with 1, so we will connect reference with 0. Then 1 is connected with 2, 2 is connected with 3, and again 3 is connected with reference, so we will connect the reference in this way. Okay, so in this way we can draw the graph. Now let us give the numbering to these elements. So we will number the elements in this way, 1, 2, 3, and this will be 4. Okay, now as per our rule we have E, N, B, L. So E will be 4, N will be also 4, branch will be 4 minus 1, that is 3, and link will be 4 minus 3, that is 1. So let us try to keep 1, 2, 3 as branch and check whether our rule gets satisfied or not. So what is the rule? Rule is, while taking the branches, all the nodes should be present and there should be no closed path. So let us remove this 4th element and check whether the rule is getting satisfied or not. So yes, all the nodes are present, 1, 2 and 3, as well as there is no closed path also. So therefore 1, 2, 3 can be taken as branch. So if 1, 2, 3 is branch, then obviously the last one should be link. So that we will draw by the dotted line, and in this way we have completed our graph. Now we have to write all the values which are associated with this particular positive sequence reactance diagram here and start our solution for the Z bus using algorithm. So I will write here one by one values. So values, you can see the first value is 0.1 J, because 1 and reference in between this is 0.1 J. Then this is also 0.1 J. Then from 2 to 3 it is 0.2 J, and again 3 to reference it is 0.1 J. So in this way we have written all the values which are associated with this graph, and now we can start finding our Z bus by using the algorithm technique. So